So centripetal force proportionality type problems, you have your equation mv squared over r. This one is referring to m, this one is referring to v, and this one is referring to the r. You only change what they're asking you. So the second problem, centripetal force, all right, originally is 8. What is this new force going to be if radius is doubled? So radius is on the bottom, so this one is what we're going to change because it's dealing with the radius. So if radius is doubled, we're going to make that a 2. They didn't tell us anything about the mass or the velocity, so we're going to keep them chilling as 1s. 1 squared is 1, times 1 is 1, 1 over 2. All right, so you're going to be left with 1/2 of the original force. The original force was 8. So what's 1/2, guys, of 8? Good, 4. Again, original centripetal force is 8 newtons. What happens if the linear or tangential speed or velocity, if that is now doubled? Well, v is now doubled. So we're going to make that 1, because it matches with v, and make that a 2. Nothing about the mass, stays a 1. V, we're taking and making a 2, but we have to square it. R doesn't change. 2 squared is 4. 4 times 1 is 4. 4 divided by 1 is 4. So we're going to have 4 times the original force. The original force was 8. 4 times 8, 32. What's going on? The centripetal force of an object. Okay, what if the mass is halved? So the mass, that 1 is now going to become a 1/2. So the m1, that becomes a 1/2. V didn't change, so it stays a 1. R didn't change, it stays a 1. 1 squared is 1. 1 times 1/2 is 1/2. 1/2 divided by 1 is still 1/2, or 0.5. So you're going to do 1/2 of the original force. The original force was 8, so what's 1/2 of 8? 4. What if the radius was cut in half? So remember, the radius is the bottom one. They didn't say anything about the masses or the velocity, but underneath here becomes a 1/2. 1 squared times 1 is going to be 1, and 1/2 on bottom, all right, is 0.5. 1 divided by 0.5 in a calculator comes out to be 2. So you'd have 2 times the original force. The original force was 8. What is 2 times 8? Correct, 16 newtons. What if the linear or tangential speed is halved? So the one on top right, with the squared, that is v. Mass doesn't change, it stays v1. V, they said, is going to become a 1/2. Remember, you only square the velocity. So 1/2 squared, you throw that into a calculator, is 0.25. Times by 1 is 0.25. And then 0.25 divided by 1 is equal to, God bless you, 0.25, or 1/4. 0.25 times the original force. If the OG force was 8, 0.25 times 8, comes out to be 2 newtons. So you guys are going to have a quiz tomorrow. Some of this will be on your quiz. Quiz is going to be about 15 questions. All right, it's going to be a little bit of this. It's going to be a little of universal gravitation, which we're going to talk about today and a little bit tomorrow. This is from the other day, Monday, when we looked this on the notes. I spent some time explaining this. All right, if all these were moving in a circular path. Okay, the bar would start here. You have A, B, C, and D on it. If we just go to this part of the track here, this section of the rotation, so this bar, if it's trying to go to this point, so right here, as this whole thing rotates, do they all make the same amount of rotation? They would all rotate around. They would all make the same amount of rotations around. So the rotational speed, you'd write in same. But the tangential speed or linear velocity, what's good with that? Well, to go from where the bar is now with A, B, C, and D on it to where we're looking for it to go, how much distance who needs to cover the most distance if you're looking at that? Yeah, right? So if you were just almost thinking about it for a second as straight line, right? Object D has to move probably 5 times the distance as the inner one, A, right? So they have to cover the most distance, then C, then B, then A. So the tangential speed is the farther you are from the radius, the greater your tangential speed. So it would be D CEBA. Okay, here, rotation, you need to make sure that the object is going located, there's an axis located with inside the body of the object. So we have D. The point an object rotates around, that's an axis. So we have E. Revolution is the motion about an axis, all right? So the rotation around an axis that's located outside of the body. So we got DEH. D-E-H. The rate an object rotates around a circle, that would be your rotational speed. Your tangential speed is the speed of an object moving along the circular path. And then we have period. The period is going to be the time that it takes to complete just one complete circle, one complete lap, one complete revolution. And that would be number 6. So number 6 is letter G. Frequency is the number of revolutions or rotations per second, number of cycles per second. There's many ways to word that. All these were in the PowerPoint. And then the centripetal force, well, obviously it's the only thing that's got force in there. So there you go. DEH, CAG, FUB. So looking at the baby version of a gravitational force basics lab. How does gravity affect objects? So it says to circle or highlight objects, all right, or statements there that you think are true. Gravity, does it depend on the material of objects? What do you think? No, I agree. Is gravity a force because it can't move objects? Or gravity is not a force because it can't move objects? Yeah, so that's false. It definitely can move some stuff. Gravity is a force because it's a push or pull. Yeah, what does it do to the object? If you just drop your pen, what's it doing? Yeah, it's pulling it where? Down to the ground, all right, towards the center of the Earth. Moon has less gravity than Earth because it has less mass than Earth, or the moon has less gravity than Earth because it has no atmosphere? It's going to be because it has less mass. The atmosphere is not going to actually really play that much of a role, unless you're trying to live on it. Okay, so two things in mind here. Yep. Two things in mind. Variable, something that can be changed or controlled. Something that can be changed or controlled. Now, independent variable. The independent variable is something that can be changed. All right, so an independent variable is something that can actually be changed by the person actually running the experiment. Okay, something that can be changed. All right, what is tested, what we manipulate, what we alter. And then the dependent variable is, all right, what's going to be affected. All right, what's affected by the change. So this is what we're observing. This is what we're measuring. All right, and it's basically our data collected. So from here, it's basically going to tell you to go to the link, open up the simulation, and figure out some stuff. So I'm going to open it up real quick, and then we're going to figure out what variables can be found in this simulation. Okay, so that is a little loud. We're just going to turn that down. Yeah. Okay, so can I change the size of the guys? No, I can't do that. Just change the size of the sphere. Yeah, by increasing the mass. So change the mass, which shows, visually an increase in size of the sphere. And then is there anything else that I can change? Distance. Okay, so you're going to highlight or circle distance between figures. Mass of the spheres. Those are the two main ones. All right, and we can just say, all right, yeah, size of the spheres. But really, the ones that we want are mass and distance. All right. Now those are our variables. Something that's going to wind up changing is the actual force. All right, so that is going to be, I guess it's a dependent variable. It's what's going to be affected. So we can circle force, highlight force. Yep. All right, so flip to the third question. What do you think? Sure. What do you think the size of the arrows on top of each sphere represent? What do you think these arrows on the top represent? Not exactly that. We're talking the bold black vector here is good. All right. Yeah. The magnitude of the force. That's what it's going to be representing. It's going to be representing the magnitude of the force. So there's two variables that you can truly manipulate. And those are our independent variables. Our dependent variables are what's going to wind up changing. So mass. We're going to write mass here as our first one. How is that going to affect, or what is going to change based off of the mass? Okay, so let's just say this is our distance. What happens when I increase the mass? The force increases. What happens when we decrease the mass? Very good. All right, so uh, increase in mass causes an increase in force. And then we said also a decrease in mass led to a decrease in force. The other variable that we have, distance. What happens as we get closer together? Good. And then what happens when we get farther apart? Good. So distance. Okay, so when we decrease the distance between objects, this little, bless you. All right, decrease D, between. This is my little symbol for between instead of writing out the whole word, B/W. All right, a decrease, all right, in distance between objects. He's in the bathroom right now.
All right, as soon as you return. Thank you.
All right, thank you. A decrease in distance between objects is going to equal an increase in the force. So basically, the closer they are, the stronger the force between them. Now, what happens if we increase the distance? All right, so we increase the distance between them. What happens? It's going to be the opposite. It's going to be a decrease in force. So this is an inverse, all right, inverse relationship, inversely, or just let's say inverse proportion, and this is a direct or directly proportional. So if something happens to one, it happens to the other. If something happens to one, the opposite happens. So now that we've looked at that, gravity is a force that can be changed. True or false? Could we change that force? Yeah, we can. Yeah, gravity is a force that can be changed, right? By what? By changing mass and or distance. but the bigger the object is, the smaller the force of gravity. No, definitely not. That was false, right? In the sim. Okay, if we started it here and we increase the mass, all right, by increasing the mass of an object, the bigger it is, the larger the force was. Larger the mass, larger the force. Next, As one object gets closer to another object, the force of gravity will increase. True. And what was our reasoning for that? Well, all right, bringing the objects closer or shortening the distance led to an increase in force in the simulation, right? So we're just going to write in the simulation, shortening the distance increased the force. Sun has a greater gravitational force than Jupiter. Yeah. Yes, it does. What is my reasoning here? Sun has a greater what? Good. Sun has a greater mass. Ooh, easy. Notice that the size of the spheres are the same, so that means the masses are the same. So which of these two pairs has the greater gravitational force? Which one do we think? Okay, so if we're not sure, let's go to this. Let's make these the same size. Okay, the first picture is a little bit farther apart, right? The force right now is about what? Just about 20 newtons. Second diagram and on the picture shows them closer together. All right, what if they're closer together? Which one's bigger? Yeah. So this pair. All right, explain why we picked the way we did. All right, the smaller the distance between them, more force. The shorter the distance between objects, the greater the force. Hmm? All right. So the next diagram that we're looking at is this. All right, so what's up here? Which of these pairs has the greater gravitational force? Which one do we think here? If they're the same distance. Yeah, the first one. There's no trick question there. All right, same distance. But the left pair has a greater mass. All right, but the left pair has greater mass. Why do you think Saturn and Jupiter have more moons than the other planets in our solar system? They have higher gravity to trap them. All right, but why do they have higher gravity? They're large, which means they would have a large mass. Very good. All right, they have a higher gravitational force. All right, they have higher gravitational forces than the other planets. They have higher gravitational forces than the other planets to trap the moons. All right, or let's see. They have higher gravitational forces than the other planets because of their large mass. All right, or because they have the two highest masses of our planets. Because they have the two highest masses, which allows them to hold, and I mean in quotations, right? To basically using their force, gravitational force, to hold on, or to hold on to several moons. And the last couple questions here. Can gravity be considered a force? Yes. Evidence. Force is a push or pull. And you saw the arrows. You saw the arrows in all of these. They're all going towards. Why is this not right? All right, all the arrows are going towards the other. They're always pointing inward. All right, so yes, it is considered a push or a pull. As long as objects have mass, they exert an attractive force on one another. All right, the arrows are pointing inward for both. In both scenarios, you have the arrows pointing inward. What variables affect mass or affect gravity? Mass and distance. Those are the only ones, right? We could change in the simulation. So by changing those variables, we change the force of gravity. And our reasoning there, well, mass was directly proportional. All right, it led to an increase. Or as we increased the mass, the force increased. All right, if we decrease the mass, gravitational force decreased. And then it is inversely proportional to the distance between the objects squared, which leads us to Newton's law of universal gravitation. All right, you have two masses involved. It's what we would call an inverse square law. So the two dudes on top, they're cool, they're chilling. All right, multiply them together. All right, we increase them, we're going to increase gravity. We decrease them, we'll decrease gravity. Big G is a constant. Big G, all right, is 6.67 times 10 to the negative 11th as our value. Very, very small number. And the distance between the objects squared. So distance affects this more than the masses do. Big G is in every single one of those problems, so we don't really pay attention to it. It doesn't matter for us. But, all right, D squared, because it is squared, it affects, all right, our gravitational force exponentially. So when we, all right, shrink down the distance, all right, the force increases dramatically. Almost like thinking about holding two magnets super, super close together. When they're super close together, you can really, really feel that pull, right? With two magnets, and then like the farther apart you get, it's like super, super weak. All right, so the distance really is going to play a big, big role in that. So getting on to the next portion here, universal gravitation problems. So with this, all right, remember that, guys, when we were drawing free body diagrams, F sub g was your weight. That was your weight. It was your gravitational force acting on an object. So little g, all right, is essentially how we figured that out for Earth is by doing, that's a little too big. Let's see if we get a little different color. Does it shrink a little bit? Yeah. By big G times mass of the planet by the radius of the planet. All right, so when you're on the surface, by multiplying these two things, or these three things, you essentially can getting 9.8 meters per second squared. But 10:05, please. 10:05? Yeah. Okay, the true value is 9.8. We're just using 10 because it comes out to give us a little bit cleaner calculations. But that's where the 9.8 actually comes from. Mass of the Earth times what we deem the radius of Earth squared, also times big G, and we come out to get us a value of this, 9.8 or 9.81. Okay, now you see this equation. Since big G is a constant, all right, it's gravitational constant, we're going to pretend like it's not there. We're not going to do crazy big numbers, but we're going to use, all right, the M1 and M2 as M1, M2, and D as, all right, D down here, converting them all to ones. So we can do just like what we did earlier on that first assignment, we're essentially doing now. So it says two objects of a fixed mass. Okay, they're moved apart. They are now separated by 3 times their original distance. What is the gravitational force on them now? So did they change the masses at all in that problem? No. So M1 is going to stay a 1. M2 is going to stay a 2. Now, they increase the distance between them by how many times? By 3 times. So D, right, see how D is right there? On the bottom, that's our D. And we're going to square that. So we're going to make that 1 a 3, but it has to be squared. What's 1 times 1? And what's 3 squared? Bing bong, 1/9. And that would be your answer for the first one. So you'll get questions like what we did earlier, review-wise, from yesterday. And you'll get some questions like this. This one, a 50 kg student standing on the surface of Earth attracts the Earth with a force closest to, what would basically the weight of this guy be? So I wrote the equation Fg is equal to mg, m, 50. All right, little g, we're using as 10. What's that number? 500. Yes, 500. And the unit for any force, newtons.
That's it.
That was it. All right, now they're saying, hey, you got a distance of a meter. Cool. It separates two masses that are equally sized. That's just how they start off. So now they're just basically saying if one mass is doubled, what happens to the gravitational force? So this would be M1, M2, and D. How many masses changed? Only one of them changed. So we can make it, it doesn't matter which, technically, if there's only one that changes. So the first one I'm going to make a 2 because it says it doubled. So 2. The other mass doesn't change, so we keep it a 1. And they didn't change the distance, so we keep that a 1. 2 times 1 is 2, and 2 divided by 1 squared. 1 squared is 1, so 2 divided by 1 is still just going to be 2. 2 times greater, my friends. That's it. This is cake. A space probe has a mass of 5 kilograms on the surface of Earth. What is its mass placed on a location where gravitational acceleration is 2 meters per second squared? Trick question. Remember, if you were right now to teleport to the moon, Are you going to be the exact same? Yeah, you will be the exact same person, right? You made up of the same material, so your mass doesn't change, but your weight would change because gravity would change. But it's a trick question. Mass would be the same, so what would your mass be? It would still be 5 kilograms. An astronaut, mass of 60, and has a weight of this. You're at a different location. Solve for G. Okay. So if F is 12, M is 60, U2, solving for G. How do I get G by itself? Yeah, you got to divide both sides by 60. 12 divided by 60, 0.2 meters per second squared.
Where did you get 2 from?
What? What do you mean? Where did I?
Where are you divided? The 60, you divide by 60 to get 2 by itself.
Yeah. So like it's basically like if I said, 3 is equal to 9x, how do I get x by itself? You got to divide both sides by 9. It's pretty much what we just did. You get G by itself. That's all. Planet X, twice the mass of Earth and twice the radius. If your weight on Earth is 500, what would your weight on this new planet be? Okay. So it has twice the mass. So we're going to make one of these m's a 2. And it has twice the radius. So the other mass didn't change. And it has twice the radius. So the r underneath would become a 2. But what do we have to do with the r underneath? Square it. 2 times 1 is 2. 2 squared is, we can reduce this to, so 1/2 of the original gravitational force. The original gravitational force was 500 newtons, right? They said if your weight on Earth was this, what would your weight on the other place be? What's 1/2 of 500? Correct, 250 newtons. Okay. An imaginary star, Z, has 1/5 the radius of Earth. So R, I'm going to make 1/5. 1/5. But remember, that has to get squared underneath. And it's 1,000 times Earth's mass. So we're going to make one of the m's 1,000. And nothing else. All right, the other thing is a 1. They said the original weight of an object is 1 Newton. So what in the hell do I do? Okay. So guys, all right? 1/5. 1 divided by 5. Is 0.2. I have to square that. You see what it became? 0.04. So I'm going to keep that on bottom. 0.04. And what's 1,000 times 1? Good. So I'm going to do 1,000 divided by my 0.04. And what does that come out to be? 25,000. All right. Times greater. So if the original FG was 25,000 times the original FG, if the original FG is 1, I'm just doing 25,000 times 1, which is my 25,000 newtons. If a satellite moves in a circular orbit around a planet, the satellite would have a constant what? Displacement. velocity, speed, or acceleration. So this is kind of going back over a few different units. There's the center. Here's the object. If this thing is rotating clockwise, so if I have a point here, that's my velocity vector. The acceleration vector is always pointing inward. What is displacement defined as? Correct. How far you are from where you started. So do you think that's going to stay constant? Nope. Velocity. If we move the object to here now, is velocity constant? Is acceleration constant? They're the same number. They're always pointing inward, but look, are those two arrows pointing in the same direction technically? So yes, it can have a constant speed. Yep, it can have a constant speed.
What's the last answer?
Speed. All right, and so pretty much what we just did on the front, guys, is like what you'll do for these here. All right. Just tell me what happens if the distance between is quadrupled. Nothing happens to the masses up top. So you have a 1 and a 1. If the distance between them quadrupled, so that's a 4 squared, be 1 times 1 is 1, and 4 squared is 16. 1/16 of the original force. And you go on from there. And then the next one, you're doing the same thing, but then you multiply what you get here. So if you've got 1/16, you multiply that by the object here. So let's just go through this one. If one of the masses is tripled, remember, these are the masses up top. So only one of them is tripled. Make the first one a 3. The other one doesn't change. They didn't say anything about the radius. So what's 3 times 1 divided by 1 is still 3. So it would be 3 times the force. If the original force was 60, 3 times 60, 180 newtons. All right, so that's what you guys have to finish. Please.